When you think of sugar, you likely think of the small white crystals that we sprinkle in our food or in our beverages in order to sweeten them. These sugar crystals are made of simple, small sugar molecules. However, these same sugar molecules can also be built together into much larger and complex sugar molecules, such as in our starches and carbohydrates that are in many of our food products, but then also into polymers like cellulose that makes up the cotton fibers that we use in our clothing. These incredibly diverse sugar molecules are all possible due to a nucleophilic addition reaction between alcohols and carbonyls. So our sugar molecules will include both alcohol functional groups as well as carbonyl functional groups, and we can then take these individual sugar molecules and link them together to create all these different complex molecules that we find throughout our natural systems. So to begin this reaction, we can start with any aldehyde, again with my R representing any generic carbon-based structure, and we're going to react it with an alcohol. Again, I'll use R to represent that this could be any kind of carbon structure on our alcohol. I'm going to label this as R2 and this is R1 so we can distinguish between these two different carbon chains. And we're also going to include an acid here. So we have our alcohol and our carbonyl here, and the alcohol is going to add on, as with our other nucleophilic addition reactions, it's going to be adding on to either side of our double bond. So we're going to be adding on the hydrogen from our alcohol on one side, and then we're going to be adding on the oxygen and our carbon chain on the other side of that double bond. At this point now, we've formed a new functional group. This is what we call a hemiacetal. So we started from our aldehyde here, and our product now no longer has that carbonyl carbon-oxygen double bond. So this is actually a new functional group. It looks kind of like an alcohol, but it's an alcohol that also has another bond to an oxygen, with then, of course, another carbon chain attached to it as well. So we're going to call this a hemiacetal. Now at this point, we're actually not done with our nucleophilic addition reaction. We can actually continue to react with our alcohol. I'm going to use the same alcohol, bring in a second unit of that alcohol, still with our acid catalyst. And we're going to attack that carbon again, add on a new unit of our alcohol. And in this case, now we're going to add on that second alcohol unit at the top. And so we have 2 units of our alcohol added on to our original aldehyde carbon structure. Now again, we've modified it from our hemiacetal functional group that had the hydroxy group and our oxygen carbon chain here. Now we have a full acetal. So our acetal is a carbon connected to 2 oxygens that are connected to carbon chains. So this is essentially a double ether, right, where we have these 2 different ethers attached to the same carbon. Our hemiacetal is halfway between that full acetal and our original aldehyde, right? It has 1 oxygen connected to a carbon chain and the other in a hydroxy group. Now we can take the same reaction and do it with a ketone as well. So if we have a ketone, that means we have our carbon with 2 different carbon chains on either side. So then when we react it with our alcohol, I'll mark this as R3 because it could be another unique carbon chain. We're again going to use an acid catalyst. And now we produce a very similar structure, but you'll notice we have a small difference here, right? We add on our hydrogen on one side of the double bond, we add on our alcohol on the other side, and when we compare this new compound with the hemiacetal before, you'll notice the key difference is that our central carbon has no bonds to hydrogen, right? We have 1 hydrogen up here in our hemiacetal, but 2 bonds to carbons here in our product that came from our ketone. So this is very similar to our hemiacetal, but we're actually going to give it a different name. It's going to be a hemiketal. So that ketal name indicates that we came from our ketone, whereas our acetal name indicates that it came from an aldehyde. And we can also see that based on the difference in the number of carbons attached to that central carbon there. Again, as with our hemiacetal, this is just a stopping point on the way to our final product, which is going to be that full acetal or that full ketal here in the case of our ketone. So again, we add on another unit of our alcohol. We're using an acid catalyst, and we get our full ketal product where we have now our original 2 carbon chains attached, as well as our 2 ether-linked carbon chains from our alcohol. So you can see how we're able to add on that alcohol to our existing carbonyl compound in the same way that we're so you can see how we're able to link. So you can see how we're able to take our alcohol and link it together with our ketone to create a larger molecule here in our new ketal or acetal functional group. So again, it's the same kind of thing that our sugars do as we're wanting to link those together to make our larger, more complex. Let's take a look at the mechanism of this reaction so we can learn a bit more about how this works. So we're going to start off with our aldehyde here in this case. So I'm going to be making a hemiacetal and then a full acetal here. And of course we have our acid catalyst. So the first step is going to use the nucleophilic nature of our carbonyl. This reaction is going to look pretty similar to what we do with our acid catalyzed hydration of our carbonyl. So first we protonate. So we protonate that oxygen up there. That's going to lead to our protonated product here, the positive charge on that oxygen. Now at this point, our oxygen wants to gain more electrons, and so we're going to bring in our nucleophile, which is our alcohol. And our nucleophile can attack our carbon here, which is of course our main electrophile of our carbonyl. And at the same time, it's going to free up our electrons here to move up to our oxygen to eliminate that positive charge. Again, so far this is exactly the same as our water hydration of our carbonyl. So now we have our alcohol produced at the top. We still have our original hydrogen that our aldehyde had at the beginning, and we have our alcohol linked on down here. Now at this point, this alcohol has a positive charge. Again, we want to try to eliminate that. So we're going to take the water that we make from our acid here. We bring in that water molecule, and we can take off this hydrogen so that we eliminate the positive charge of our alcohol. So we have a deprotonation step, and now we're producing our hemiacetal. So again, up till now, every single step has been exactly the same as what we saw for our acid catalyzed hydration of our carbonyl. The only difference is that we're adding on an alcohol instead of just our water molecule. Now again, our hemiacetal is really just an intermediate. We can form hemiacetals, but they're generally going to want to react further to get our full acetal. It's not that they're unstable necessarily, it's just that the reaction to go forward to the full acetal is more favorable than sitting here at this hemiacetal in most cases. So to get to our hemiacetal, we had 3 key reaction steps. We started off with protonation. That prepared our carbonyl for the nucleophilic attack, which of course is our second step. So we attacked with our nucleophilic alcohol. And then of course in the third step, we're just deprotonating that alcohol in order to get our initial product. Now to go to our full acetal, we're essentially going to repeat these same 3 steps. So we're going to start off with our protonation. So we bring in our acid catalyst. Note this acid catalyst was actually regenerated in our third step here of deprotonation. So we just regenerated our catalyst by taking a hydrogen here. And we're going to use our OH group of our alcohol. And we're going to take off that hydrogen in order to create our positively charged alkyloxonium ion that then acts as a good leaving group. So from here, as I mentioned, my H2O right here is a great leaving group, so this can break off. At the same time, we can move these electrons down to help to stabilize our carbon here. All right, when this water breaks off, that normally makes an unstable carbocation. But since our oxygen here has excess electrons, we can move those electrons in to stabilize that carbocation. So we eliminate that water and we form a new structure that looks fairly similar to our protonated carbonyl structure from the reaction pathway to our hemiacetal. All right, so notice the similarities between our compound up here and our compound down here. The only difference is that here we have that extra carbon chain attached from our alcohol, whereas up here this was our original carbonyl oxygen that of course had no carbon chain attached. So now at this point, we can do our nucleophilic attack of our second alcohol unit. So we're going to bring in another unit of our ethanol. We've got, of course, that high electron density on our oxygen. So we can come in here, attack our carbon, that's electrophilic, shift those electrons up to our oxygen. Again, we're essentially repeating this nucleophilic attack step. That takes us to our intermediate, tetrahedral intermediate with our two alcohols linked on. But of course we have a positive charge up here since we still have our hydrogen attached. We broke our double bond down here, so now we just have our alcohol linked there with that single bond. We also have our water molecule that broke off at this step. So we can bring in that water molecule, use it as a weak base, and we're going to deprotonate to give our electrons back to our oxygen, and this will create our full acetal product. So we have the carbon chain that we started with on our aldehyde. It's just a single carbon in this case, and we have our two alcohols, one linked on at the top, one linked on at the bottom, and we've created our full acetal molecule. Again, we normally don't really stop at the hemiacetal, but continue on to create our full acetal product. Of course, at the same time, this water here is pulling off that hydrogen, and so we're also recreating our acid catalyst. Again, that's the definition of a catalyst. A catalyst always has to be regenerated or not consumed in our reaction. So whatever catalyst we use initially needs to eventually get regenerated in our reaction. So for our last few steps of the reaction, so we had another protonation step where we prepare now our hydroxy group to be a good leaving group. We then followed that up with the one unique step in our second half of the reaction, which was our elimination of that water molecule. So we eliminate our water molecule here, and now again we're just repeating our same two steps up there. We have our nucleophilic attack with our second unit of our alcohol attacking. And then, of course, after our alcohol attacks, we always have to do our deprotonation in order to remove the hydrogen that's attached to that alcohol. So again, protonation, nucleophilic attack, deprotonation, just like the first half of our reaction, the only new thing is our elimination step. Now, one thing that you should notice here as we look at this is that you could really argue for all of these steps kind of going in the reverse direction as well, right? There's not really a clear reason to add our hydrogen onto one oxygen as opposed to another, right? We're always going from one positively charged oxygen to another positively charged oxygen. So in fact, all of these steps are reversible. We could push it in the forward direction, or we can push it in the reverse direction fairly easily. The question is really just going to be, do you have more of your alcohol, right? Because if we have a lot of our alcohol reactant, that's going to push it forward, following our usual equilibrium expression. Whereas if we have more of our water, then that will push us back in the opposite direction. So it's really just a balance of how much of your alcohol do you have, how much of your water do you have. You can add excess alcohol, push it forward to make your full acetal, and then add excess water and acid to push it back to your original carbonyl, whether it's the aldehyde or the ketone, depending on what molecule you need at the time. The reversible nature of this reaction to our acetal or ketal allows us to use it as a protecting group. So a protecting group is a way to modify a functional group so that it then becomes less reactive and is protected when we try to then react a different functional group on the same molecule. So in this particular molecule here, we have two different functional groups, our alkyne and our aldehyde. If we add an alcohol and our acid, we can react that aldehyde into our acetal. So we're going to take that same structure. So our alkyne is unchanged, but our aldehyde is actually going to react with the two alcohol functional groups on this diol, and we combine it together to form an acetal. Right, so we've linked it now together here, and in our acetal, so we have our acetal functional group right here, with of course our carbon there bonded to those two different oxygens that are bonded in carbons. This acetal essentially, it looks a lot like an ether, right? Both of these are basically just two separate ethers connected to the same carbon. Ethers, as we know, are relatively unreactive. In particular, they don't react with bases, and they also don't react with nucleophiles. So no reaction with bases or nucleophiles. And so now our aldehyde is effectively protected, right? Originally, aldehydes, of course, they react in a wide variety of different nucleophilic addition reactions. Once we've reacted it to our acetal, now it's safe against reactions with bases or nucleophiles. So now, since our acetal is not reactive against bases or nucleophiles, we can react with our alkyne without worrying about our aldehyde, which is now our acetal functional group, reacting under the same conditions. So we can add in our sodium amide, which of course we use for deprotonating our alkynes. We can add in our alkyl halide, and we can complete an alkylation reaction, which will not react with our acetal itself. So we can add on those extra carbons to our alkyne, and meanwhile, our acetal will stay exactly the same. At this point then, we just have to add our excess acid and water, and we can hydrate this back to our original aldehyde. So our alkyne was safely reacted in that alkylation, whereas our aldehyde remains the same. It's protected by that acetal functional group. So this is a common mechanism to use whenever we have an aldehyde or even a ketone that we don't want to react under specific conditions. We can kind of hide it temporarily inside an acetal, and then after we've reacted the other functional group, we can convert it back to our aldehyde or even our ketone in order to then have our original functional group back. So this nucleophilic addition reaction is very helpful both in a biological sense of allowing us to link those sugar molecules together between our carbonyls and those alcohol functional groups, but it's also very helpful for us as chemists too, especially in its use as a protecting group. So we'll see both of these very frequently, again, both in biochemistry and in the lab as we're working with our carbonyl molecules.